Hi! In this video I will finally use the formulas we've developed for TC in the last videos to compute TC in the first case, namely the case of the finite field Fp with p elements. After doing this computation, which is in some sense the most fundamental computation in the field, we will draw the consequence that we can consider THH as a sort of cyclotomic chain complex. This relates heavily to pioneering work of Kaledin on the subject, but there's a lot of subtleties involved which I try to explain. So this second part can be skipped on a first watching this lecture series, but in terms of general understanding I feel that it adds a lot to why cyclotomic spectra and why not working in the derived category in chain complexes. Hi, I'm Thomas Nikolaus from Mathematics Münster. In order to calculate TC of Fp, let's recall how we defined or computed TC as a general formula. So if R was a ring, or more generally a connective ring spectrum, I guess we could even allow a scheme, but we decided not to go into that too deeply here. So then what was TCR? TCR was just the TC of R, the spectrum TC of R. Topological cyclic homology was just the equalizer TC minus of R of two maps from TC minus of R to TPR pro-finitely completed. One of the maps we called phi and one of the maps was the canonical map. So let's remember what these maps were, where I guess the easier map is the canonical map. The canonical map is just the map from TC minus R, which was just THH R, H as 1, the homotopy fixed points on HT, and then we just have the canonical map to THH R Tate T. The one, Tate by construction is a cofiber of a map into this guy. So we have this canonical map, and then of course this is TP, and then we go to its pro-finite completion. A product over all P completions, and that's the canonical map, which we denote can here. And what is the map phi? The map phi is a map TC minus R into TPR. And to see that this exists, we just write this as a product over all primes over THHR Tate CP HT. So that was the theorem we explained in the last lecture, that those are canonically equivalent. And I guess this depends heavily on the connective bounded below assumption on the cyclotomic spectrum THHR. And then under this equivalence, then phi is given by, well, it's a map into a product, so it's a family of maps, and we just take the phi p's, which are mapped from THHR to THHR Tate CP, and we raise them to the HT. Okay, so that was the definition or theorem how TC can be computed. And I should maybe mention that historically TC was defined differently by Beckstedt, Chiang, Madsen, but this formula, which I proved with Peter Scholze, simplifies the way you can compute TC. Okay, same is actually in fact true, same for X, the cyclotomic spectrum with X, the underlying spectrum bounded below. Bounded below. For example, connective. Okay, then you just replace THH everywhere. And so the example we want to run today is Fp, field with P elements, P prime. Then what did we have? We have computed that TC minus Fp was given by the P at x adjoint two variables xt modulo xt equals P. And so x was a variable in degree 2. It's the Beckstedt element which came out of THHFP. And T is the periodicity generator of, or I guess I shouldn't call it periodicity generator, it's the generator of the homotopy fixed points of S1 acting trivially on the integers. Okay, and those two guys survived and we had this result. And then we also found that Tp star Fp was just a localization of Tc minus at the element T. And I mean, this was just given by Zp adjoint T plus minus. Right, because once T is a unit, then you can rewrite X as Pt to the minus 1. And I guess this then automatically agrees with its profinite completion, because in this case, if something is already p-complete, then the profinite completion, which is the product of all completions at all primes, will just agree with the p-completion, because all the other completions are 0. So this will agree with the profinite completion, I guess. Okay, let me not. So as a result, Tp Fp agrees with its profinite completion, and we can just sort of forget the profinite completion in all the formulas over there. And now our two maps, can and phi, from Tc star minus Fp to Tp star Fp are ring maps. This is because all the, I guess I didn't say it here, but all the constructions involved were sufficiently lag symmetric monoidal so that these are actually ring maps. And now we want to compute what they do. So given that they are ring maps, both of these are algebras over Zp, we just have to figure out what they do to X and T. Right? And for Can it's easy. So Can, why is it easy for Can? Because this identification, identifying Tc star minus as a localization at T, is along the Can map, right? This is what came out of our spectral sequence calculation. So what we have is, I mean, this is why we call it Can, or sometimes it's even denoted identity, which doesn't quite make sense because it doesn't go through the same map, but it just corresponds to the inclusion or the map from this guy into the localization, which actually on homotopy is an inclusion. So what we have here is, in other words, what I'm saying is Can of T is equal to T. And accordingly, Can of X is going to be given by P T to the minus 1, right? So that's what we said. When we localize, the reason we can forget X is that we can rewrite X in terms of T. Okay, so that's a Can map. And I guess I should also say on coefficients, it's the identity, right? It's just a ring map from Zp to Zp. But now we want to talk about whether or not, I mean, what phi is. So what is phi? So the lemma is that there exists a unit, alpha, in the p-adic unit, such that phi of x equals alpha t to the minus 1. And then accordingly we have that phi of t, so the second statement is basically a consequence of the first, because in here we have the relation xt equals p, and of course this has to be respected. So if phi x is alpha t to the minus 1, then phi of t has to be alpha to the minus 1 pt. Okay, so that is the lemma. And before I prove the lemma is one remark as an order. We will prove the lemma in this form, but with some more care, with some more work, one can show that in fact alpha equals 1. So this might be the easier thing to remember, even though we won't quite prove this. So it turns out that phi just sends x to t to the minus 1 and t to pt. Right? This is somehow quite the opposite to the canonical map, which sends t to t and x to a p multiple of t minus 1. Okay, proof. Let me prove the lemma in the form we stated it though. So what we want to do is we will have the following diagram. We have the following commutative diagram. Where we have TP, FP, then TC, I want to look at the map TC minus FP here with my map phi. And then I can also, I do have the, this is THH FP Tate as 1, and we have this map from THH FP down to FP, which came out of the fact that THH FP was a colimit. It's basically FP to the tensor T. So we have a map like this from FP Tate T. And maybe I should say that. Induced from THH FP down to FP, which was a T-equivalent map. And so, okay, now we can go down to THH FP. So what is this map? The upper guy is just the homotopy fixed points of S1 acting on the lower guy, and that's just the structure map of this homotopy fixed point. So the forgetful map, which forgets that we're here in the homotopy fixed points and here down in the spectrum itself. And of course, by construction, we can put this guy here, Tate CP, because as we said, the upper guy is just the homotopy fixed points of the lower row, and even the map is just the homotopy fixed points. And then, of course, here, in order to complete the square, we just have to say that here we go to FP Tate CP. Okay. So where, in fact, this is also the forgetful map, because we've seen that FP Tate T is in fact FP Tate CP HT. So under these constructions, these are all maps which forget homotopy as one fixed points. And now we want to chase our element T through this diagram. So let's first introduce some notation. So clearly, remember we want to look at this map from TC minus into VP T minus 1. And we have, by definition, in degree, this is a ZP in every degree. So we can write phi of x has to be alpha t to the minus 1, and phi of t has to be mu t. Right, and everything is about showing that alpha is in fact a unit. Now let's take, chasing t element tc minus in degree minus 2 of fp through the diagram. Clockwise, it is 0. Why is that? Well, I guess clockwise we follow it through here, from here to there, but here we see that this already is connective, THHFP, so in degree minus 2 it's necessarily 0. This is in fact the only connective term, right? So all these terms are periodic. All these 4 terms are 2 periodic, and so here we follow it through. The counterclockwise composition is, well, I guess if we write this, we can write this as fp adjoint t plus minus tensor, maybe an exterior algebra for odd t, maybe an exterior algebra exterior algebra on a degree -1 generator for odd p, and I mean at prime p equals 2. This is given by fp, maybe let me write it as s plus minus, where s is in degree -2. Anyways, in degree -2 this is an fp, and the claim is that this is just given at the class of mu in fp. Right, mu is just an element which tells us where t goes. And why is that? Well, I mean, for this you just follow here. So in degree -2 this is zp, then you go to another cp by mu. And this map then, what does this do? Well, this map will just send, in fact, the degree -2 generator to the degree -2 generator here. Why is that? Well, you just see on the homotopy fixed point spectral sequence, or in fact the Tate spectral sequence, you just see that this is a generator. Here we had the generator T in degree -2. Right? We just lifted the generator from FB Tate T to here. So this will just send it. And in fact, even, I mean, if you're a little worried about how canonical these identifications are, for everything I'm going to do, I just show stuff up to units anyway. So it wouldn't really matter if it was multiplication with some unit. Anyways, this is fp in degree -2. Here it's just a reduction, and then this map, I mean, this is just a statement about group cohomology. So we're in negative degree, so this is just a range where this is group cohomology or cohomology of the classifying space. BS1 and here BCP, and then in degree -2 this is an ISO. Just an easy little calculation in terms of that classifying spaces or group cohomology. And that shows this claim. Okay? But in particular, what does this mean? So thus, well, since the diagram commutes, we know this is 0, i.e. mu is divisible by p. Mu is equal p mu prime. But then what do we get from that? We can write pi as p as phi of p, but this is then phi of xt. Right, because in TC minus we have the relation, oh man, I should have written xt equals p. Sorry for that. So then we have this relation, but this is then of course phi x times phi t. And this is now alpha mu, which is also p alpha mu prime. And this is an equation in the p-adic, so it turns out that alpha mu prime is equal to 1, i.e. alpha a unit. And also then, of course, mu is given by p alpha to the -1. Okay, and that shows the claim. And again, of course, this only shows that we have this unit, but with some more work one can show that the unit is 1, but this will actually in fact be irrelevant for our computation of TC, which is what we want to do now. We now compute TC by the long exact sequence associated with the fiber sequence. Which fiber sequence do we have? Well, I guess we have the fiber sequence TC goes to TC minus goes to TP. Phi minus CON. Right, and this gives us a long exact sequence on homotopy groups, and that's what we want to use now. So let's see how this fiber sequence looks like. Well, I guess maybe I hope I get my board work straight. So here I want to write TC0 FP. And this then goes to TC minus 0, right? But that is just a copy of ZP. And then again I go to TP0, that's another copy of ZP. I'll write what the map is in a second. So this goes to TC minus 1 FP. And then here we go to 0, right? Because TC as well as TP are 0. And then here we go to TC minus 2 FP, and then we end up in TC minus 2, which is ZP generated by t. And then here we again have a map to zp generated by t, and so on. And so on and so forth. And let's see what, and I guess up here we have 0, 0, tc1, fp, and then here we have a copy zp generated by t to the minus 1, and here we have a copy zp generated by x. And then we have tc2. And so on. Right? So, okay, so the next guy, well, you know. Okay, so this is how our long exact sequence looks like. And let's now identify the maps. So these maps here, this is the map phi minus p, right? I guess what's the order I wrote it? Phi minus can. Phi minus can. But what is it in this degree? I mean, this is strictly speaking true for all those maps. What is it in this degree? Well, this is just the degree 0. This is 1 and 1. So both maps are ring maps and then 1 to 1. So in this degree, it's in fact a 0 map. Right? And what is it in this degree? Well, in this degree, we just have to figure out, what did we see? Phi sends t phi, the map phi sends t to, what's the best way to write that? I mean, so maybe, what's the best way to write that? It sends t goes to alpha to the minus 1 pt minus t. That's how the map looks in this degree. So it's basically given by, i.e. it's given by multiplication with alpha to the minus 1 p minus it. Okay, so this is it as a map from zp to zp. And what is the map here? The map here is in fact actually what happens here. I guess in this case we just sent x goes to, now what did phi do? Phi sent it to alpha t to the minus 1 minus t to the minus 1. Okay, and I guess what happens in the higher degrees we just get more copies of alpha to the minus 1 p here, right? Because we have t squared and so on and so forth. So you see all these maps are basically, all the non-degree 0 maps are of the form I guess up to a unit zp to zp identity minus p times alpha. Right? I mean, I guess it's not always the same alpha. Sometimes it contains further copies of p. Maybe I should not call it alpha. Let's call it beta. Okay. Right. And now, at this point, I claim that all these maps are in fact isomorphisms of abelian groups. So this is something I want to leave for you as an exercise. Proof that all those maps for every copy of beta are isomorphisms of abelian groups. And we will focus on the consequences of that now. Namely what TC is. So what have we proven? We have that TC star of Fp equal to. So now let's see. I mean, all these maps and all the negative degrees, so that it's periodic, are isomorphisms. So there's no contributions here. But what do we get here? I mean, this map is 0. So that as a kernel has a ZP and as a co-kernel has a ZP. So we get TC0 and TC minus 1. And all the other terms are 0 because all those maps are isomorphisms. So we get that this is ZP for star equals 0 and minus 1 and 0 else. Okay, so That is the result. And that's the first computation of TC. And I mean, you see how strikingly simple it is. I mean, we went through all this Bergstedt periodicity and spectral sequences, TP, TC minus, and only to eventually arrive at this simple result. And now a bunch of remarks are in order. First remark is, as a ring, I mean, after all, TC is a ring. Of course, we can write, I mean, there's not much choice. TC of Fp, I mean, since it is concentrated in 0 and -1, it has to be an exterior algebra. So it's going to be Zp epsilon modulo epsilon squared equals 1. Epsilon squared equals 0, where epsilon is a generator in degree -1, a generator of TC -1. One can wonder, though, what it is as a ring spectrum. It's a ring spectrum with two homotopy groups, and the claim is one can show that, and I will not, that TC of Fp is as an E-infinity ring. It's equivalent to the Eilenberg-MacLane spectrum of the p-adix to the S1 as an E-infinity ring. So for example, this tells me something about the C0 operations. It says that SQ0 is the identity. Right, so this is not immediate. I mean, one way to deduce it is to use some sort of flat descent and deduce it from the computation of Fp bar, which we will do in our next video. Okay, so that's the first statement. And the second statement is that Quillen has shown that the p-completion of algebraic K-theory of Fp is, so what he proves is that the p-completion, the homotopy group of the p-completion of algebraic K-theory, which I denote like this. So this is just pi star of, I mean, we didn't talk in this course about algebraic K-theory, but that's also a spectrum. And then you p-complete that. So that's the characteristic. Then this is actually isomorphic to Zp star equals 0 and 0 else. So as a result, we see that TC, I mean KFP, Zp is in fact equivalent to the connective cover of TC of Fp. Right, because the moment we take the connective cover of TC, which has two homotopy groups, we're only left with one homotopy group, and it's an Eilenberg-MacLane spectrum, and it agrees with that. And so in fact, we see that TC is kind of close to equivalent to K-theory up to taking connective covers for Fp. And this sounds a little funny at this point, admittedly, because, I mean, both are after all just sort of, I mean, have one or two homotopy groups. Doesn't seem like a big deal, but this is in fact the beginning of why trace methods really work well. So that's the most important computation in terms of that. And by the way, trace methods, I mean, this works well at the characteristic of the ring and not away from the characteristic. So if you know a little bit about K-theory, you know that K-theory of Fp is more complicated away from the characteristic, and TC stays the same though. So that's a method for computing stuff at the prime p. Okay, I guess now we ran the calculation of TC of Fp, and now I want to draw some theoretical important consequences from that. So the computational part of this video is over now, and we're just running computational consequences of that. Right. Okay, so corollary. There is an E-infinity map HZ into TCFP. And secondly, as a result, TCA is an HZ module spectrum for each FP algebra A. Well, the proof is just, I guess, connective cover is a map HZP to TCFP, right? Because in degree 0 it's just FZP, and then of course we can map from HZ to HZP. And for the second part, we just note that TCA is a module over TCFP, right? Because everything involved was black symmetric monoidal. And the claim is, since A is an FP module, in the category of algebras, say in Abelian groups or more generally in spectra. And so I didn't even assume that A was commutative. Even if A is not commutative, it's just a FP algebra, then I mean it follows that by Lex monoidality of all the functors that TC is an HC module spectrum. And remember that being an HC module spectrum is quite a structure, right? I mean basically HC module spectra are equivalent to chain complexes. So we're saying that TC is something algebraic. It's a chain complex, and all chain complexes, so as a spectrum it decomposes into the Eilenberg-MacLane spectrum on its homotopy groups, the product of all the Eilenberg-MacLane spectra on the homotopy groups. So it has no K invariance, if you know what these words mean. Okay, and now we draw further consequences of that. One can make a more highly structured statement about than the fact that TC is an HC module spectrum. We will even want to say that THH is. And in order to say that, let me sort of state a proposition. So we have an adjunction TRIF. So TRIF was this functor which took a spectrum and considered it as a cyclotomic spectrum. So that was the thing where we just equipped our spectrum with the trivial action, and then we could just go with the map. So maybe I should say that X upper TRIF is the cyclotomic spectrum with trivial T action, and the map, the cyclotomic Frobenius, is just going from X to XHT, HCP, and then with the Kann map to X Tate CP, phi. So I guess we introduced this for the sphere, but you can just do this for every spectrum, in fact. And so I guess you have to take a little bit care as to why this is a T-equivalent map. I think this was an exercise in the video about cyclotomic spectra. And this just works. Okay, so this gives a functor from spectra to cyclotomic spectra. And here I have TC, which is a functor from cyclotomic spectra to spectra. And the claim is that this is an adjunction. Okay, so where, I mean, of course, means the upper one is left adjoint to the lower one. Okay, and this proposition I want to leave as an exercise so that you can check whether you understood the definition of TC and how the category of cyclotomic spectra works. As a hint, you should prove that, I mean, you should use the fact that colimits in cyclotomic spectra are computed underlying, and that X upper TRIF is the tensor of sphere upper TRIF tensor with X. Okay, so just go through this exercise. then we have this adjunction. And I mean, there's more true, and this I just want to use as a sort of black box. So the left adjoint is symmetric monoidal. I mean, this is clear because, I mean, tensor product of cyclotomic spectra was just underlying. So we just have this construction being underlying. I mean, this is a ring map or like a lag symmetric monoidal transformation. And I mean, in general, it's true that the right adjoint of a symmetric monoidal functor is actually lag symmetric monoidal. But we already know that this is true. The right adjoint is lag monoidal, lag symmetric monoidal. But we already know that TC is lag symmetric monoidal, so this gives another proof of that fact. But sort of, if you take it independently, this is claiming that there's a compatibility between the symmetric monoidal structure on this guy and the lag symmetric monoidal structure on this guy. Okay, so what does this mean? Corollary. We have a map of cyclotomic E-infinity rings, by which I just mean ring objects in the infinity category of cyclotomic spectra, commutative ring object, E-infinity ring objects from HC TRIF into THHFP. So by the previous adjunction, and so by my extension that the adjunction is sufficiently compatible with ring structures, giving such a map out of the left adjoint in THH is just equivalent to giving a map from HC into TC. And that's just the map we've constructed over here. And again, there's a relative statement saying that for each FP algebra A, THHA is naturally a HC TRIF module. And if A is commutative, then it's even an HC TRIF algebra. Okay, so that is an abstract consequence of our computation of TC of FP. Right, and at this point I want to issue a warning. And the warning is the following. I guess this statement doesn't sound that exciting at the beginning. I mean, after all, we know that THH FP is just an Eilenberg-MacLane spectrum no matter what, because it's a module over FP, right? We have the map from HFP into THHFP, and this makes it a module. And in fact, this is an algebra map. So saying that THHFP is an HC module is not in some sense doesn't sound like a deep statement. On the other hand, this statement saying this in the category of cyclotomic spectra means it's compatible with everything we have, right? Cyclotomic structure and so on and so forth. And that actually turns out to be a much deeper statement, as it, for example, also implies that TC is an Eilenberg-MacLane spectrum, which in general is just way far from equivalent. I mean, for example, the map FP into THHFP can't even be made S1 equivalent, right? Because on S1 homotopy fixed points, we already don't have P equals 0. So in THHFP, the element P is not equivalently 0. But more is true, actually, that this map is totally different from the other map I just sketched. Let me say that. So the map HZ into THHFP from the previous corollary is different from the map, from the obvious map I guess maybe we call this map F, just to give it a name. So that's a map. It's different from the obvious map. We can just go from HZ with projection to HFP, the mod P reduction. And then we have this I, this inclusion into the colimit. A structure map. And maybe we call this map G. Even as maps of spectra. So, or maybe I should erase the even, because the second one is just a priori a map of spectra. I guess I could say it's a map of ring spectra, but certainly not in any sense a map of cyclotomic spectrum. And in fact, it's easy to see that you cannot make this map into a map of cyclotomic spectra. But I'm saying that, I mean, in fact, you will see that, for example, by saying it's not this map, because essentially there's not so many maps here. As we know, such a map, if we gave that the drift structure, would have to come from a map into TC. But I'm saying that these two maps, which look very innocent, it's just a map from HC into an Einberg-MacLane spectrum, another map from HC into an Einberg-MacLane spectrum. But the claim is that they are highly different. And this is something which can be very confusing because, well, I guess in ordinary algebra, if we make something in module over the integers, I mean, that's no datum at all. In homotopy theory it is, because, I mean, the integers is not the initial ring. So as a result, it might be a little bit confusing. But let me argue why these are different. So to see this, we show that post-composing the two maps with the following map is different. So with the map which we call R, that's a map from THH FP. Just as a spectrum, we have a map phi into THH FP Tate CP. CP, and sorry, I might skip the P. Before I denote this atomic structure with phi P, but at this point we're just P complete, so we're just focusing on that one, because for all other ones the target would be 0. And now we have this, again, this map from THHFP down to FP, this bottom cell map. Okay, this map R, and we show that the postcomposition with blah are different. I.e., refers, if we postcompose F, this is not homotopic to postcomposition with G, which then of course showed that the two maps are non-equivalent. In fact, we've just seen that the cyclotomic, let me not say that. And in order to see that, we'll sort of consider diagrams. So one, for the map G, F, consider the diagram. So we have, I mean, by construction, we have a map of cyclotomic spectra from the TRIF cyclotomic spectrum, which has this TRIF map here as a structure map, and then we go down to THHFP with the cyclotomic Frobenius, Tate CP, phi. And then of course we can also go down to FP Tate CP, right? And I mean, I guess this is our map R, right? So this outer composite is our map R. But now we see that we can also take this road through the diagram. And now the point is that what is this composite? So this composite just factors through going from HC to FP Tate CP. But I mean, this is just, I mean, this composite is just by construction of our map. This is just a projection to the Tate CP. So I mean, it just arises as sort of applying Tate CP to this map, so if we take this map and go down to FP, right? This is just a map from HC to HFP, which necessarily has to be the projection map. So this map is just this map, I guess, which I didn't write in here, to the Tate CP. So this is just projection to Tate CP. Thus RF is equivalent to the composite HZ goes to HFP, and then with the drift map here, HFP Tate CP. So I guess I could have said that in 2 steps. First step is that it's equivalent to the drift map here and P Tate CP, but then because of the naturality of the drift map, it's also equivalent to this composite, where this is a projection map. Okay, so that was how we can identify RF for here, and now we want to go to identify RG. Consider the diagram. So consider the following diagram. Consider the diagram. So what we do is we can go from HFP. Here we have our bottom cell map. Right, so, and then we can, or the inclusion, Tate CP with the cyclotomic Frobenius. And now by construction we had a diagram where we put HFP tensor over the sphere, HFP Tate CP here, where this is then just the multiplication including the inclusion induced up the CP equivalent map. And now if we go down here to HFP Tate CP, what is this composite? This composite is just a composition. This was a Tate diagonal. This composition just includes here, and then, I mean, the composite from here to HFP without the Tate CP down to HFP, this is the multiplication of the ring spectrum. So as a result, by construction, this composite is just the Frobenius, the E infinity Frobenius. E infinity Frobenius. So this is a map that exists for every E infinity ring spectrum and plays the role that the Frobenius homomorphism plays in ordinary algebra, but in a higher algebra. And if you want to learn what this is, we briefly mentioned that at the end of our higher algebra video on the Tate diagonal. So where Achim mentions the existence of this map. And so this shows thus RG is equivalent to the composite. Well, we go from HZ with P down to HFP, and then with the Frobenius, the E infinity Frobenius. Frobenius. I mean, we usually also denote this phi, but maybe I should for a second not denote every map by phi to avoid confusion. Okay, so at this point we see, in order to answer our question or show that these two are not equivalent, it actually suffices to show that the map TRIF and the E infinity Frobenius are not equivalent after precomposition with P. And so at this point we need to use something about this E infinity Frobenius, which is the theorem. And I mean, it's a little hard to say who to attribute the theorem. I guess, I mean, it's really, I guess Achim already mentioned in the video that the E infinity Frobenius has to do with power operations. Once you establish this connection, then, I mean, it's really a theorem of Steenrod. But I guess in this form that I stated, or more precise form, it appears in my paper with Peter Scholze, but I think it was indicated to us by Jacob Lurie, and I guess, yeah, I don't really want to take credit for that. Just that we sort of figured it out or wrote it down in this exact language. Okay, so the claims is the maps TRIF, HFP, TCP, and the Frobenius, the E infinity Frobenius, which is HFP, TCP, differ by all the C0 operations. What do I mean by that? I mean, we know that HFP TCP is just a two-periodic spectrum. And so what we're looking at here are maps from HFP into a bunch of copies of HFPs in even degrees. And we know what these maps are from HFP into copies, upshifted copies of HFP, and these are given by C0 operations. So what happens is that, I mean, under this equivalence here, using the TRIF map, if you use the equivalence using the TRIF map, then TRIF is just going to be the inclusion in the degree 0 part, so there's no higher maps. And then this map, this Frobenius, will contain all the possible C0 operations. So I guess at the prime 2 it hits all the factors, and at other primes it will only be only get sparser. But anyways, so it differs by all the possible C0 operations. So all the C0 operations show up, and I mean, the way I'm stating the theorem is really the better way to say, not compare an absolute map, because then you have to identify the target somehow, but to say that the difference of these two maps is the C0 operation. So again, I mean, a precise statement involving degrees and everything can be found in my paper with Peter Scholze. But I mean, as a corollary, we have that RF is not homotopic to RG, i.e. F not homotopic to G. And this is just because, I mean, the C0 operations, if I post-compose them with a reduction, are not zero. Okay, so that was the warning I wanted to issue about this map from HC TRIF into THFP being a highly non-trivial map. And let me just conclude by restating this statement about being an HC TRIF module in the following way, which might appeal to some people more algebraically inclined a little more, which is the following. Let me make the following definition. We define the infinity category of cyclotomic chain complexes or the cyclotomic derived category would maybe be a more appropriate name, cyclotomic DZ as the pullback I mean, pretty much the same way we define cyclotomic spectra. We just do just replacing spectra everywhere by DC. So we just go to P and P, DZ, BT, upper delta 1, P and P, DZ, upper BT, cross DZ, upper BT. And then here we just put DZ upper BT. In other words, what I'm saying is a cyclotomic chain complex, and I should give the maps here, I guess. This is source cross target, product, and this is just a map which sends identity, comma, blank to the Tate CP, and then the product of all primes. So, in other words, what I'm saying is a cyclotomic chain complex is just given by an object a chain complex with a action of T and a map C to C Tate CP for each P, which is equivariant. Pretty much the same way as the cyclotomic spectrum, I'm just saying like chain complex or object of DZ everywhere. And now the point is the following. So, proposition. So, a category of cyclotomic chain complexes. And by the way, maybe I should have mentioned, I mean, obviously you can just give that definition for any nice enough stable infinity category where the Tate construction makes sense. We just apply it to chain complexes. So the statement is that the category of cyclotomic chain complexes is in fact the module category in the symmetric monoidal infinity category of cyclotomic spectra over HC TRIF. And, right. And this I want to leave as an exercise. And of course, this is, I mean, what I want you to do is, I want you to just think about what it means. I mean, remember how the tensor product of cyclotomic spectra was defined and think about what it actually, in concrete terms, I mean, maybe neglecting coherences just informally, think about what it means to be an HC TRIF module in cyclotomic spectra. And see, using the fact that HC modules are the same as chain complexes, you should, or the derived category of C, you should somehow try to convince yourself that this is a true statement. And of course, I mean, giving a rigorous proof of that, you'll require some technology of higher algebra. So for those people, those of you who are familiar with higher algebra, I recommend giving a careful, clear proof of this. I mean, this can be basically deduced from abstract statements and this kind of TRIF adjunction that we had before. But yeah, for just convince yourself why this is true. Why somehow this tells me that being an HC TRIF module not only equips the underlying spectrum with an HC module structure, but also makes a Frobenius HC linear. And so as a corollary, we have that for an FP algebra A, THHA is canonically, naturally, an object of, well, cyclotomic chain complexes. Or it is the Eilenberg-MacLane spectrum of an object in cyclotomic chain complexes. And as we've seen before, this is a highly non-trivial statement. And again, as a last warning, this category does not describe, I mean, you might think this is algebra, right? Tate construction, everything is in algebra. But the problem is that, of course, Hochschild homology, just ordinary Hochschild homology, not topological Hochschild homology, would be an object in here, DZBT. So it's just a chain complex, an object of DZ with a action by T, but this does not allow for such maps. So Hochschild homology cannot naturally be made into a coherent chain complex, a cyclotomic chain complex. Okay, so that was as much as I wanted to say about abstract consequences from the calculation of TC-FP. In the next video, I'm going to compute TC for perfect rings of characteristic P. Thank you very much.